Welcome to Synapsis. I'm Gökçe Özdemir, a biomedical scientist specialized in neuroscience. In biology, synapsis is a stage during cell division where chromosome pairs line up before exchanging genetic information. And for me, synapsis is a bridge to make medical science more understandable for everyone. Thank you for being here. Let's dive in. This episode will take you back by a few years and remind you of how your advanced human body and human cells can be weakened and appear to be almost useless when faced with a strong microbial challenge. In 2019, Mother Nature reminded us how she can change our lives with only one virus infecting one person in China, and that resulted in a pandemic which put the entire world into crisis mode. At least 7 million people died as a result of COVID-19. Though there are studies that claim the full impact of the pandemic has been much greater, with estimates of up to 18 million deaths from 2020 to the end of 2021, with more than 650 million documented cases, though the real total was likely a lot more because many cases just weren't reported. It affected nearly every country and territory in the world and spread every instance an infected person breathed, talked, coughed, or sneezed. It also spread through aerosols, which are tiny particles that linger in the air, and also by touching surfaces contaminated by the virus. I do apologize for reminding you of the days of stocking up on disinfecting wipes and sprays to clean everything you touched. Not my greatest memories either. The culprit was the SARS coronavirus 2, which stands for Severe Acute Respiratory Syndrome Coronavirus 2, simply because number 1 was already taken back in 2002 by the SARS outbreak that also emerged in China. SARS-1 affected 26 countries with over 8,000 confirmed cases and around 800 deaths. The responsible virus for both these outbreaks are different, but they belong to the same family of viruses called coronaviruses because they just have a crown-like appearance under a microscope. Viruses are grouped into families based on their genetic material, how they replicate, and their overall structural characteristics. And there are about 168 virus families. You can maybe imagine how fun this makes microbiology classes. And once under the same family, there are still many factors that distinguish them from one another, including their pathogenicity. The 2002 SARS-1 virus was much more deadly than SARS-2, but SARS-2 spread more efficiently, partly because it was better at transmission before symptoms appeared, or even in those who didn't show any symptoms despite being infected. You could even call it smarter than SARS-1 simply because it was better at spreading and therefore at staying alive rather than killing the host quickly before having a decent chance to spread. They are genetically 80% identical, but the remaining 20% was more than enough to give them very different behaviors. Once inside the body, they both use a protein called ACE2 receptor, which stands for angiotensin converting enzyme 2 receptor. It's a receptor that respiratory tissues in particular are quite rich in, hence the lung getting its lion's share during the illness. The more ACE2 receptors in a tissue, the more ACE2 protein binding, and in the case of COVID, the more opportunities to infect that specific tissue as the virus travels in the bloodstream. You can think of a receptor as a lock to enter a place, and anything that binds to it as the key that provides access. The key has to be specific to the lock, and in this case, the virus had a perfect fit for the ACE2 receptor lock. Once unlocked, the virus is welcomed inside the cell, and it has an immediate mission upon entry to hijack the cell's machinery to make more copies of itself to keep spreading. No ACE2 receptor, no entry for this virus. Normally, this ACE2 receptor does wonders for your health. ACE2 is critical for balance in vascular function, By binding to its receptor, say in the lung, ACE2 helps reduce inflammation, reduce pulmonary hypertension and vascular permeability, and even helps inhibit cancer cell growth. The virus binding to ACE2's receptor instead of ACE2 causes the receptor to be internalized along with the virus, and this reduces the number of available receptors on the cell surface. This means less ACE2 to counterbalance the inflammatory effects of angiotensin II. Long story short, this binding not only allows for the virus to enter the cells, but it makes the infection significantly worse by disrupting your body's own protective pathways, making the virus quite smart for going after the ACE2 receptor when you think about it. All this talk about ACE2 might remind you of ACE inhibitors used to treat high blood pressure and heart failure. And you might think, if ACE2 is so good, why do we use ACE inhibitors for treatment? Because ACE1 and ACE2 are different enzymes and they have opposite roles. ACE1 converts angiotensin 1 to angiotensin 2 and acts as a vasoconstrictor that increases blood pressure, stimulating inflammation. And ACE2, as mentioned before, does the exact opposite. ACE inhibitors block this first type, and that's why they're so beneficial. Now, coming back to what the virus does once it's inside the cell. How does this viral hijacking work? And I hate to say this, but be ready to get scared of how smart viruses can be. So, first off, viruses aren't really alive in the traditional sense. They can't do anything on their own. They need a living cell, whether that's a human, animal, plant, or even bacterial cell. Once they find a cell to infect, there is their super powerful ability. They can hijack the cell to turn it into a little virus factory. When a virus gets into your body, it's like an intruder breaking into your house and forcing you to make its dinner, clean its house, and do its laundry. Now, this sounds pretty bad already, but it gets worse when we mention that they don't just invade and destroy cells. They're also quite sneaky and evolved all sorts of ways to hide from your immune system. They do their dirtiest works when undercover. Take herpes viruses, for example. Many types of them, but you've probably heard of type 1, which causes cold sores, and type 2, which causes genital sores. These are so incredibly good at laying low in your body. After the initial infection, they retreat into the nervous system, where immune surveillance is less intense. And they just hide, staying dormant for years if they wanted to, waiting for the right moment to reactivate. Usually happens when your immune system is weak, like during stress or illness. And then, boom, your sores are back. And once you've got herpes, unfortunately, it's with you for life. There will absolutely be an episode in the future about herpes and HPV, since they are the most common sexually transmitted infections, and they unfortunately don't have a cure. HIV will undoubtedly accompany them, but for now, let's use HIV as an example here to discuss some undercover operations of viruses. HIV relies on rapid mutations. The virus creates small but incremental genetic changes to alter its surface proteins to continuously outpace the immune system's ability to recognize it. Imagine you're trying to track down someone with a yellow hat, and all your systems are looking for the yellow hat. And without you even noticing, the suspect just threw away the hat or changed it with a different colored hat. This is called an antigenic drift. The virus mutates to evade the immune system, which is one of the reasons why vaccines and therapies are so difficult to optimize for HIV or influenza even. They continuously outpace the immune system's recognition abilities. This is exactly what happened with COVID when new variants kept emerging. In extreme cases, antigenic shifts can happen where entire gene segments get swapped and create entirely new viral strains. An example of an antigenic shift is the Spanish flu in 1918. A genetic reassortment happened between an avian influenza virus and a human-adapted influenza strain. And this antigenic shift created a virus that caused approximately 50 million deaths worldwide. That's right, 50 million. 50. And it doesn't end there. Viruses not only keep changing their genome, they can also manipulate your immune system markers to make it appear as if there is no active infection. They can mimic your very own host molecules to appear like they belong there. Very much like putting on an invisibility cape straight out of Harry Potter, or wearing a school's uniform and going to classes when you're not even registered. And there you have it, an arms race at the molecular level, where even a single point mutation in a viral genome can tip the balance in favor of the invader, and you find yourself in an extremely toxic relationship. All these complicated mechanisms aside, there's actually another very simple reason for why we can't just take a pill for a viral infection. As I mentioned, viruses have to hijack living cells to operate. They have to not only find the cell, but also find their way to inside the cell by binding to a receptor. And this is why you can't really kill a virus without also killing your own cell that got hijacked. Bacteria are different. They live and reproduce on the outside of our cells, making them easy targets for antibiotics, which can be designed very specifically for proteins in the cell walls of bacteria. They're easily distinguished as foreign, and both an antibiotic and the immune system can find the bacteria without killing any human cells. This might make you think of the fact that there are antivirals out there. So how can they be effective? The first issue is that antivirals need to be much more specific than antibiotics, and not just specific to the virus type, but sometimes even to different stages of the virus. Some drugs block the receptor the virus uses to enter the cell. Others target the enzymes the virus uses to replicate itself once it's inside the cell, while others prevent the virus from releasing its new viruses before they can be spread to the body. For example, medications for HIV don't eradicate the virus, but keep it at undetectable levels. Or an antiviral for herpes or chickenpox can suppress outbreaks, but they can't completely remove the virus. Since all that requires immense resources to figure out, many antivirals in the market work simply by boosting the immune system and letting it do the work of killing the virus. This is why when you have the flu, your doctor often says, "There's no cure for this, you just need to rest and take some vitamins, it'll go away on its own." Different viruses are much more different from each other than bacteria are. An antibiotic is like a mechanic who can fix various brands and models of cars with the same set of tools. Each car is different, but the engines and the parts are generally similar, or the differences can be figured out. Viruses, on the other hand, are like robots from a Terminator movie, using their own intelligence to constantly change their form. You might develop a drug to break off the robot's arm, but then the robot learns how to cause damage without using its arm. Now that we know to take viruses seriously, let's come back to our main topic. COVID very quickly showed that it was capable of infecting a lot more than the respiratory tissues, and that its symptoms were multisystemic. Even after the initial illness, it could linger and continue to impact your health thanks to its ability to spread widely in the body and just stay there, sometimes even reactivating other pathogens you might have from before. This is called long COVID, and a conservative estimate is that 10% of infected people got it, the highest percentage of diagnoses being between the ages of 36 and 50 years, and numbers show that vaccinations were very effective in preventing long COVID. Having pre-existing conditions, on the other hand, like type 2 diabetes, obesity, connective tissue disorders, or ADHD, These have been identified as risk factors for long COVID, with females also at a higher risk compared to males. Symptoms can persist for weeks, months, or even years after the acute phase of infection and can affect many organs, from the lungs to the gut, your heart, blood vessels, kidneys, liver, brain, pancreas, immune system, and lo and behold, your reproductive system. And you can probably tell by now that this widespread effect is because of the widespread expression of ACE2 receptors in the body, which is not really surprising considering how important ACE2 is. Some common symptoms of long COVID are general fatigue, shortness of breath, brain fog, frequent headaches, joint and muscle pain, digestive issues, mental health issues, and so on. A popular complication is also myocarditis, which is the inflammation of the heart muscle. Looking at reproductive health, there were and still are a lot of concerns about the impact of COVID on fertility. Naturally, these concerns still result in new studies that try to answer two questions. At least this episode only cares about two out of many questions that are still being investigated about COVID. 1. Did the virus itself impact fertility? And 2. Did the vaccines made for the virus impact fertility? In conspiracy lingo, was the virus or the vaccine made to control the world population? I know that sounds like a fun question to talk about, but no conspiracy talk today, and probably ever. Just science. Bummer. I'd love to give you the answer right away, but I've already been talking for a while, and we haven't even scratched the surface for both male and female fertility. So I'm afraid this will have to continue next week. But before you go, I will give you some spoilers. Reproductive systems of both men and women were certainly affected from COVID infection, with or without vaccination. But current data shows these effects to be largely temporary. I won't spoil what these effects are and whether vaccines independent of an infection impacted fertility or not. To find all of that out, while also learning some anatomy, make sure to come back next week. And until then, stay informed, stay curious, and make sure to subscribe. Santé!